Hi everyone, thank you so much for coming to today's seminar. My name is Christopher Perez. I'm a junior at Harvard College studying computer science and statistics, and I'm also a course assistant this semester for CS50. Today's seminar will be focused about the introduction to data science and machine learning in Python. So today's outline for the seminar includes a brief discussion about what is data science and what is machine learning more generally. In the machine learning section, we'll talk a little bit about some of the most popular tools employed in today's machine learning world. And then the second half of the seminar will focus on an interactive example with a real data set using Spotify most streamed songs. And then finally, we'll conclude with looking ahead at some resources and then some next steps that you can use to help use data science and machine learning in your own CS50 final projects. And so the purpose of this seminar is to sort of more broadly introduce you to the key ideas in data science and machine learning. And so hopefully you can employ some of these tools or techniques in your own CS50 final project that's coming up pretty soon. Great. So with that, we'll go ahead and get started with talking a little bit about what exactly is data science. So data science is the process of gathering, analyzing, and interpreting data to uncover patterns, make informed decisions, and predict future outcomes. And one of the really cool things about data science is that it is indeed a multidisciplinary field that combines statistics, data analysis, and then also machine learning, which I'll talk about in a few minutes. One of the great things about data science, right, is that it is not just confined to like one little sphere or bubble. So it is very interdependent on many statistical ideas, data analysis, and we'll soon see some specific machine learning techniques, which in turn allows for a lot of really cool real-world applications for data science. Some of these include route optimization. So if we're thinking, for example, about shipping an Amazon package from point A to point B, how can we sort of employ traffic patterns and customer information to sort of optimize and shorten the path from point A to point B so that package arrives in the shortest amount of time possible. Other real-world applications include revenue forecasting. This is especially important for companies trying to use like time series data to be able to sort of see how their growth trajectory is for their revenue. And then also election forecasting, so sort of seeing polling electors, voters in states, countries, to sort of see how candidates are performing. So that is the brief overview of data science. And now we're going to be talking about a typical data science workflow, like a typical day in the life of what a data scientist does with data science. So the first key step that we like to do in the data science workflow is first to define our problem. When we first start collecting our data and sort of analyzing, before we even do that, to begin, we want to sort of clearly define our problem statement, sort of the objectives that we want to address in the data collection and data analysis part, and also sort of outline our key assumptions that we have prior going into our data collection analysis section, and then be able to use those problems, those objectives, and those prior assumptions and sort of either confirm them and validate them or sort of challenge them throughout this process. The second step to this data science workflow is then the data collection process. Now this could be either a pretty simple process where we can either get the data that we want pretty readily accessible on Google, for example, or this might be a more lengthy, involved process and also possibly costly as well, where we have to go out and seek our own data. And then in this process, right, we always want to make sure that we are sort of collecting valid data, which I'll now talk about, which leads to the data cleaning and preparation part. So in the data cleaning and preparation part of this data science workflow, right, we're given this data, and now the question is how do we go about sort of analyzing the data and sort of drawing key insights and conclusions from this. Before we can even do that, we need to first clean the data. So what I mean by this is that the data that we're given may not always be correct. There could be, for example, missing values. There could be extraneous values. There could be outliers. So before we can even begin to employ machine learning models and sort of draw insights, we want to be able to make sure that we sort of purge our data of these outliers, of these anomalies, so that we could draw the most valid conclusions possible from the data that we are given. And then the next step, which is called exploratory data analysis, or EDA for short, is a very popular step in the data science workflow where now we're given this cleaned data that's been prepared for us to sort of analyze. And now we want to sort of draw and gather like summary statistics about this data. So in this step, the key goal is that once we draw and gather these like summary statistics of the data we've just collected, sort of drawing like preliminary results from this data. So for example, this could include looking at like the mean, creating box plots of the data to sort of see what do like the quartiles, like the 25th percentile, 75th percentile, what do the median sort of look like with the different parameters involved in the data, to sort of see how the data is distributed, like is it normally distributed, is it maybe skewed to one direction or the other. So this step is pretty key in sort of understanding the data that we've collected thus far. The next step is feature engineering. So this is very dependent on the human themselves. And in this step, in the data, we are given like predictor values. And in the feature engineering step, what our key goal is to sort of maybe go beyond the predictors that we've been given in the data and sort of maybe combine them in new ways and creating new features, new variables from the data that we've been given. So for example, this can look like creating new variables that are, for example, like linear combinations or scaled combinations of the different predictors that we've been given, and then using those new features that we've sort of engineered, then being able to create new variables and then be able to create statistical machine learning models based off of those. The next step, once we've sort of analyzed preliminarily the data and created some new features, then comes the model development phase. So I'll talk a little bit more soon in the machine learning section about some specific models that you may want to employ in this process. But in the model development phase, we could test one model, two different models, a variety of models. In this step, it's very dependent on clearly what problem you seek to gain or uncover and solve in this data science workflow. And so in this step, the next step would then be like the model evaluation. So in the model evaluation step, we're sort of using different hyperparameters, tweaking different features and variables in the models that we are creating. So for example, this could be like the number of epochs that we're training on. This could be like the learning rate, for example, or number of clusters if we end up wanting to cluster our data. So in this model evaluation step, as we are tweaking these parameters, we're sort of gaining these like metrics of success, which could look like, for example, F1 scores or recall for that matter. So as we're testing these different hyperparameters, we're seeing how well does our model compare to like ground truth models or ground truth values that we've given it at the beginning of the problem of this like workflow, and then seeing how well it does. And then from there, being able to adjust our models based off of how well we are performing at each step in like the model development process. And then after we've sort of evaluated our models, now is like the deployment stage where now we could deploy it to like the public, to different users who may want to use our models for predictive results and outcomes. And then finally is the monitoring and iteration step. So once we've deployed the model, it isn't just enough to just deploy it and then call it a day, right? So after we deploy, right, we always want to consider monitoring and then iterating based off of results from users. So for example, the key here is that we want to make sure that our models generalize well to data that it hasn't been trained on or hasn't seen throughout this like data science workflow in the previous steps. So in this step, what we're really trying to do is ensure the long-term scalability of our models and ensure that they perform reasonably well with new unforeseen data that we may have not considered before in previous steps. All right, so now we're going to start talking about some different machine learning techniques and the different subsets of machine learning so that you can gain a more thorough understanding of what it takes to go about the machine learning process. So what is the goal of machine learning? The goal of machine learning is to imitate the way that humans learn to gradually improve accuracy. So what we're doing here in machine learning is we're taking computers and we're trying to mimic the way that humans think, the way that they act, to sort of be able to draw better conclusions from the data that we're given, draw new insights, and hopefully be able to understand our data all the more better. And then in the machine learning process, this involves the application of different statistical, mathematical, and numerical techniques to derive some form of knowledge from data. So if you're familiar with some different machine learning techniques beforehand, from before the seminar, then you'll know that a lot of the machine learning techniques have a very statistical, mathematical, especially linear algebra foundation that is important in sort of creating these models from the ground up using a mathematical framework. Machine learning is also very dependent on human intervention. So for example, determining the set of features that we're using and also understanding the data input that were given originally. And this could be either like good or bad. So when we're doing machine learning and creating models and assessing data, we always want to be cognizant of the sort of biases that we as humans can introduce into the model selection, the feature engineering, and the overall data science workflow that I discussed previously. And then also, just as a note, machine learning powers some of the most innovative technologies that are used today. So for example, more specifically, in the realm of like Netflix and Spotify, it's used to personalize recommendations. So for example, for song recommendations, or even like TV show or movie recommendations based on what you as a user have watched previously. It's also used for fraud detection in banking and also predictive healthcare analysis. So it has a lot of really important applications that are used today, hence why the world of machine learning has risen in fame so much recently. Now we could break up machine learning into 3 subsets. So what we have first is supervised learning, we have unsupervised learning, and we also have reinforcement learning. So to begin, what is supervised learning? In supervised learning, we are given a collection of data with inputs and predictors that map to specific like ground truth like labels. So in the process of supervised learning, the key goal here is to be able to sort of learn a mapping from these predictors to ground truth values that we could sort of use in our models to be able to predict different values. So one of the key methods here that is very basic, although very popular and widely employed today, is like linear regression. So in a linear regression, what is happening here is that we have a collection of independent variables, and then we want to sort of be able to create a conclusion on a dependent variable. So in this process, what we do, one of the goals is to minimize, for example, least squares loss. So what this looks like is sort of, if we create the line of regression from our data and sort of get like the best coefficients for that matter, if we draw the residuals between the line that we've created, the line of best fit for that matter, and the individual data points, the key goal here is to sort of minimize the size of those residuals. So that's like the least squares loss. So the goal as we create this line is sort of to be able to minimize this least squares loss so that we could sort of have like the least possible error possible. So for example, we can use least squares regression to be able to predict housing prices given certain predictors such as maybe population density within a city, for example. And then the second supervised learning method that we have is classification. Classification comes in many flavors in supervised learning, but one of the more basic classifications that we can consider is sort of a binary classification, where we have 2 different classes, class A and then class B. So recall that in supervised learning, we're given data where we know the labels, where we know the classes of the given data. So the goal here in classification then is to draw a decision boundary between these 2 classes. And the goal here is to minimize like the 0 to 1 loss. There's other different types of loss, but what I'm going to be talking about in this seminar is like 0 to 1 loss, where what that means is that if a new data point is on the correct side of the decision boundary, then there's 0 loss. But then if it's on the other hand, on the other side of the decision boundary, then that's a 1 loss. So in this classification technique, our goal, right, is then to be able to minimize how much loss we have. So hence drawing this decision boundary is a way in which we could be able to sort of minimize the loss overall and create sort of the best decision boundary for future predictions. All right, great. So now we're going to transition to talking a bit about unsupervised learning. So in comparison to supervised learning, where we are given ground truth labels for our data, in unsupervised learning, it's the opposite, where we aren't given label data and we need to sort of draw conclusions from the characteristics of the predictors that we're given to sort of be able to create new insights and see sort of how we can maybe create natural groupings of the data itself. So One of the first popular methods is clustering, and a specific clustering method technique that we have in unsupervised learning is k-means clustering, where the goal of this is that first we define k as a number of clusters that we want to create from our data. And then the goal here is to sort of minimize the variance within each of the clusters. So initially, each cluster has one random data point. And as we go through this iterative recursive algorithm, what we are doing is sort of adding new data points to each cluster, updating the centroids or like the medians or centers of these clusters, and then going more and more through all the other data points, minimizing the variance within each cluster so that we try to get two clusters, or k clusters for that matter, that are quite cleanly separated and have like minimal variance within them so that it reflects data points that are the most similar to each other. So that is k-means clustering, an overview of that. And then another technique that we have is hierarchical agglomerative clustering, also known as HAC. So in this method, we have what we call different linkage functions, which essentially what happens in this process is that each data point starts off as its own cluster, and then using this linkage function, which for example could be Euclidean distance, where we calculate the distance between two different data points in space, is then sort of using this function to sort of determine which data points are like the closest. So in the case of Euclidean distance, the data points that are closest in space, and sort of iteratively assigning data points to clusters together. So as we see on the graph in the bottom, each data point from 0 to 5 is on its own individual cluster, but then we see that they become conjoins as we move up in this graph. So one of the benefits of HAC is that we are sort of able to visualize how the clustering process actually plays out. And from this, we could be able to see sort of the methods in which the clustering works. So if we look at the data, if we have the actual data set for these data points, we could see, okay, why exactly is this algorithm clustering data points 0 to 1 first before 0 to 2? So hierarchical agglomerative clustering can be beneficial in that sense. And then finally, our last technique in machine learning, our last subset of it, is reinforcement learning. So in reinforcement learning, it's quite different from supervised and unsupervised learning. In reinforcement learning, we have an agent, we have an environment, and we have different states and rewards as this agent traverses through an environment. So the goal of reinforcement learning is then to be able to learn exactly how to traverse through this environment so that we can maximize our expected benefits, our gains from such a traversal. So I'm going to talk a little bit briefly about one specific reinforcement learning technique that we have, although I'll leave it up to you to look at some other resources outside of the seminar because it is quite complex and out of the scope for the seminar. But for example, we have one method which is called Q-learning. So in Q-learning, it's an iterative algorithm where again, we're trying to update based on the state that we are currently at, and given certain actions, we want to be able to update it based on like the expected value, the expected gain that we can get from performing that action at a specific state at a certain point in time. So this algorithm is very recursive and seeks to provide the agent the best optimal path it could take to traverse this environment to get the most rewards in the long run. So for example, some applications of Q-learning and reinforcement learning, or RL, more generally today is specifically with autonomous robots. You may have seen autonomous cars recently in the news. So those different autonomous robots employ reinforcement learning to sort of be able to understand the environment in which it is and learn from it based on penalties and rewards it can get from performing certain actions in certain environments, in certain states. So that is reinforcement learning. All right, and then with that, now we are going to transition the second half of the seminar to a hands-on example using a real data set based on Spotify's most streamed songs. So here I have a Jupyter notebook opened in Visual Studio Code, where basically what I'll show here right now is our Spotify CSV data file. So here contains the data that we have from our Spotify data set. So it contains different columns such as like track name, artist name, and also gives some information into like the number of streams, the danceability, the key, the beats per minute of each song in this data set. I would also suggest if you are working with CSV files in your CS50 final project, there is an extension on Visual Studio Code called CSV lint that allows you to sort of have the columns color-coded throughout your CSV file so that it makes it a little bit more readable for the user. All right, so now what I have opened is a Jupyter Notebook. So in a Jupyter Notebook, this is quite useful when working with different data sets and sort of trying to draw conclusions, insights from this, as it is a step-by-step process where we can create sort of different cells and sort of run each cell independently of one another so that we could sort of, instead of having to run the entire code at once, we can just basically run each cell one at a time so that we're not being too overwhelmed with the code that we have currently. So the first step in this Jupyter Notebook is importing the necessary libraries. So as you can see, I've imported pandas, which is a data processing library used popularly in Python. We have NumPy, we have Seaborn and Matplotlib, which are popular in better visualizing the data that we currently have. And we have sklearn. So in sklearn, it's a popular library for being able to use predetermined and pre-created different machine learning algorithms that we'll get to in the second half of this section. So in the first section, exploratory data analysis, as I defined previously in the seminar, the key goal is to sort of draw preliminary insights and be able to understand the basic workings of the data set that we are given. So the first step is to sort of, what we want to do in our Jupyter Notebook, right, is to sort of view the data set that we're given and sort of see like what we're working with. So pretend I didn't show you the CSV file. So what we could do using pandas is call data frame head, where data frame df, the variable, represents the data frame in which our data file, so the Spotify CSV file, is stored. So we can think of a data frame, or df for that matter, as a sort of like 2D array, where the column headers represent the different predictors that we have for the data, and then each row represents the different entries in that. So then if we call data frame head and we run that, we could sort of get a sort of preliminary understanding of the data that we are currently working with. So as we could see, we have like the first 5 rows, and then we could see sort of the different track names, artist counts, and sort of see sort of the data types that we are working with at the moment. Great, so now that we've seen sort of what the data set looks like in pandas, now what we could do is sort of take a look at some of the summary statistics that we have for these numerical features. So in pandas, what we could do is dataframe.describe. So then if we run this code, we could see that column by column, we're given, for example, the count of the number of data points in that column. We could see the mean of the data in that column, as well as like standard deviation, minimum, and then the different quartiles that we have for this data set. So here we're given like a huge table with all these data points, which can be helpful as we're going through this data analysis process and sort of seeing what we have, what we're working with. All right, great. So then, as I mentioned also in the data science workflow, we sort of want to see and sort of experiment with like data cleaning and data preparing before we can even get to the modeling process. So one of the key things that we want to do whenever we're given a data set is sort of check if there are missing values. Because if there are missing values, then that could affect the statistics that I'm showing up above, or that could affect how we are predicting certain features. So how we could check for null values is we could run the isNull function, and then sum, which basically goes through each of the columns, each of the predictors, checks if it's null, and then counts how many entries in that column have null values. Great. So then if we run this code, we can see that nearly all the columns have non-null values, except 2 columns in particular. So for example, in Shazam charts, we have 50 null values, and then in the key column, we have about 95. So now what we could do is drop these values. So there's different ways that we can handle missing values in pandas. So for example, we could completely drop them, as in get rid of any rows, any data entries that contain these null values. Or alternatively, what we could do is, for example, if the predictor is numerical, we could set those values equal to 0, or maybe even like an average of the pre-existing values, so that it sort of like smoothens out those entries with null values. In this case, what we're going to do is drop those null values. And so pandas allows us to do that pretty easily and smoothly. So what we could do is df.drop NA, and then here we could specify the subset of columns that we want to drop null values in. So in this case, we want to drop values from key. And then in Shazam charts. And then also, I'm going to add another parameter called inPlaceTrue, which what happens here is that we're specifying that once we drop these null values, that we want to modify these changes within the existing pandas data frame. So if inPlace was false, what would happen is that that would create another copy of the existing data frame and just use some more memory. So once we do that, we then want to check the number of null values, just make sure that indeed this works correctly. And then we could see here that all of the columns now have 0 null values, which is good, which is what we want. So great. So now the next step is then to now understand the distribution of some of the key features. So just for time's sake, I've already implemented the function for being able to create different histograms of these different features. So we're going to take a look at, for example, the danceability percentage and the energy of the songs that we currently have. I'll be posting the code later on, so you could run this code on your own to get a better understanding. So here, what we're going to do is now run this code, and then we can now see sort of the distribution of the values. So for example, we see danceability, we see that the valence of the song is, for example, a little bit roughly normally distributed. We see that, for example, for the distribution of instrumentalness, that is quite heavily right skewed, and the values tend to peak around 0 to 5, for example. And then similarly for acousticness, it is also right skewed and focus more on values that are near 0 to 20 for that matter. So a good nice thing about histograms, right, is that we could sort of be able to visualize sort of the distributions of the data and what we're working with. Another parameter that we could play around with here is the number of bins. So if I decrease the number of bins, we see that the intervals within the data that we currently have are sort of condensed, and so they're not nearly as fine-grained as in the case where it was 50 prior. So depending on how you want to visualize the data, how fine-grained accuracy and precision you want to get, you could change that parameter to sort of see how your distributions change as a result of that. Great. And then the next step that we want to do in this sort of exploratory data analysis is sort of see if there's any correlation or any associations between any one of the predictor pairs. So in this code, what I have here is that we create a correlation matrix between 3 different predictors: danceability, energy, and the number of streams that we have. So what I have here is that once we run this code for correlation heat map, we see that we get a value error. So let's take a look at what this error represents. So we see that, oh no, we could not convert a string to a float. And we get this long error with beats per minute, the key, A, mode, major, etc. So how do we go about sort of debugging this pandas error? So in pandas, it's typically common where the columns that you want to be one data type. So for example, the number of streams, for that matter, we expect it to be numerical, but it's not always the case that the data set we're given with has those data points within the data type that we want. So one of the nice things about pandas is that we can sort of check the column data types to see exactly what the data types we are working with. So we could do that easily by typing in df.dtypes. And then if we run this, we can sort of see the different types that we're working with. So we could see, for that matter, streams is an object, beats per minute is an integer, Danceability is also an integer, as well as valence, acousticness, etc. So the key issue here, right, is that in the correlation, we sort of need numerical values to work with. And we clearly see that streams is an object, so that's not letting us be able to perform this correlation matrix or generate that. So what we could do now is convert streams to a numeric value and then check to see that indeed that conversion was successful. So how can we do that? So we could start off with our data frame. We can then access the streams category column. And then what we can then do is call pandas and then use the function toNumeric, where it takes in the argument of the column that we want to create numerical values of. And then I'm also going to specify another parameter called coerce. Now what happens here is that if in the case where pandas is unsuccessful in sort of converting the objects of streams to a numerical like integer or float value, then what's going to happen here is that it's going to return like null values for those columns. So then what we could do then, once we run that, is then check to see if indeed the streams column has been converted to a numerical value. So that's why we're using the dType method, which returns the data type of the underlying object. So then if we run this now, we see that the data type is now a float, which is exactly what we want. So now let's try running the heat map again with those features. And so now we see the correlation matrix of these features. So we see that along the diagonal, we have 1, which makes sense because the correlation between the same variable should be 1. And then just like looking at the values, right? So we see a lot of the values, almost all of them besides the diagonal values, are like very near 1, which indicates to us that there may not be any strong correlations or associations, relationships between any pairs of predictors. So for example, the greatest correlation that we do see is between energy and danceability, which is 0.16, which suggests to us that there may be a weak association, positive correlation between energy and danceability, but it may not be nearly enough to support the notion that there is a very strong association between those two variables. Great, so now what I have here is some more code to sort of create a correlation matrix for a variety of different numerical columns. So I have here that in addition to the 3 that we showed above, we also have instrumentalness, liveliness, speechness, beats per minute, and also streams. Checking to see that the columns are numeric, and then we generate the correlation matrix. So then running that here, we could sort of see what the correlation matrix looks like between a greater variety of these features. So now we see that like in this perspective, there are some features which have a bit stronger of a correlation between them. So for example, in this entry with acousticness and energy, we see that the correlation is negative 0.55, which shows that there is sort of like a moderately strong negative correlation between those two predictors. And then in the case of a positive correlation, we have a sort of strong, like a moderately strong correlation, positive, between danceability and then also the valence. So the key idea here is that now we're sort of seeing between a greater variety of key features that we may want to model on, sort of which ones may be most important to sort of go about the modeling process to sort of tweak and sort of create the models that we want. All right, so now with that, we're going to transition over to the modeling part of the seminar. So I have some code already pre-written for us just for the sake of time, but what's going on here behind the hood is that we have the features for clustering already predefined. So we have danceability, we have energy, we have valence, etc. One of the other key parts we want to do in the model creating process is also standardizing our data. So what this means, like in terms of standardizing the data, is that we're going through each of the predictors, each of the columns, and sort of centering them to have like a mean of 0, standard deviation of 1. And the key goal of this is that if we're given predictors with different scales, so for example, some columns may have much greater values than another column, we want to ensure that those columns don't have too much weight in our model creating process. And so in the case where we didn't standardize our data, then that would be bad because then those columns with much greater values could impose a greater weight on those predictors in the modeling process, which could skew our results very significantly. So we apply that here just to avoid any of that. And then here we also employ k-means clustering, which I talked about a little bit earlier in my seminar. And then we're also printing the cluster sizes generated from that k-means clustering. And then finally, because we are clustering on such a great number of dimensions, on a great number of variables, what we're doing now is when we plot these clusters, so we can't plot like multi-dimensional data beyond like 3 dimensions, what we could do is we could reduce the dimensionality of the visualization to 2D. And how do we do that? We do it through something called PCA, or principal component analysis, which basically projects our data points in its clusters onto like the key dimensions or axes which contain or which account for the most variance in the data. In other words, these are the dimensions that are the most important in like the k-means clustering algorithm that help determine or are the most important in the clustering process. So then finally we then plot the clusters. So then if we run the code, we see that cluster 1 has the most, cluster 0 has the least. And then here we could see, based on the PCA projection, sort of how these clusters were created. So to the right-hand side of the code, we have like the yellow cluster, which is cluster 2. And we see like more or less that's like pretty cleanly separated from the other 2 clusters, albeit there are some purple or cluster 0 data points that are sort of within the realm, the space of cluster 2. And then we also see that cluster 1 is typically above cluster 0. So one thing about PCA projection is that we can also play around with the number of clusters and also the random state, right? Because k-means is a random algorithm based on the initial data points that we assign. So for example, we could play around with like the number of clusters. So if we change this to 2, we can see that the data is quite evenly split between 2 clusters. Or if we want to change this to 4, we're in the code again, and then we see how the data looks with 4 clusters. So for now, let's just keep it with 3. There are some numerical methods you can use to sort of determine what is the most optimal number of clusters to use in this process. So for now, we're just going to keep it with 3. So once we've now created these clusters, PCA doesn't really tell us too much about what are the key characteristics in these clusters, right? So when we're clustering, if we're applying clustering to a CS50 final project, right, we want to understand what are the underlying like predictors, what do those like values look like in a typical cluster, so that if we're given a new data point that maybe we want to cluster based on, we can sort of see like more generally where that like cluster, that value would be predicted into. So now, like a good step here is to calculate sort of like the mean value of features per each cluster. So how we could do that is in pandas, what we do is we get the data frame and then we use the method group by. And then here we specify that we want to group by the cluster to which the data point was assigned to. And then we want to take all the features that we used for clustering and then get the mean of those. And then we're going to print those and then see what these features sort of look like. So just taking a look initially at the data, we see that for cluster 0, for example, has the highest percentage of danceability, whereas cluster 2 has 54% danceability. So it's about a 20% reduction in danceability between those 2 clusters. And then also we noticed that like the energy percentage differs quite significantly between, for example, cluster 1, cluster 2, and also cluster 0 and 2. So what this suggests possibly is that maybe cluster 2, the songs that are clustered into cluster 2 tends to be maybe more songs that would be focused more for like studying or just more like relaxing music that may not necessarily have like the energy that songs in cluster 0 have for that matter. And then finally, to wrap this up, what we could do is create box plots for each of the features by clusters to sort of better assess the distributions and maybe see if there are any features in particular that are most significant in creating these clusters. So this code that I have here goes through all the features and creates a distribution cluster by cluster, creating a box plot, which will give us sort of information about the different quartiles, min and max of all of the different parameters that we seek to learn more about. So here are some of these box plots for that matter. So preliminarily, just like looking at this data, we see that, for example, in acousticness, cluster 2 tends to have a higher mean or median acousticness compared to the other clusters 0 and 1. Let's take a look at liveliness, for example. We see that in all three clusters, the median tends to be more or less around the same area. And we also notice, for example, for energy, the medians tend to be different, especially more so for cluster 1 and 2, which is also validated by the mean data that we were given previously. However, we do see that these like box plots do overlap with each other throughout. So we can't necessarily conclude that indeed like the characteristics are significant to each other, cluster by cluster, but it does give a good ballpark estimate of sort of the key properties or predictors that we could further explore more in future steps for clustering or other machine learning algorithms. All right, so now that we've looked at some of the key steps in the data science workflow, we've looked at some of the machine learning techniques that are commonly employed today, as well as a brief hands-on example through a real data set. Now let's look ahead and see some of the ways in which we could use these resources that I've talked about to implement in your own CS50 project. So here I have linked some of the documentations for what we've talked about in this presentation. So here I have linked the pandas documentation to learn a little bit more about the functions, the methods that you can use to help you manipulate and analyze data all the more effectively. I also have here linked the sklearn documentation. So here, this is very helpful in helping you explore different tools for building and also evaluating your ML models that you create. There's a lot more different types of models you can use through sklearn beyond just k-means clustering. So I encourage you all, if you're interested in using some machine learning models in your projects, to explore this a little bit more. In addition to some other stuff that I didn't talk about in the seminar, we also have weights and biases, also known as WMB. I'll have the documentation linked here, but essentially what weights and biases is that it is a platform to track, visualize, and optimize your machine learning experiments. So especially if you're going through the iteration process of your machine learning model creation, and you want to test different hyperparameters, you can use weights and biases to sort of see how your model is performing on different metrics of success, such as recall, F1 scores, etc., and sort of be able to use like the nice visualizations that weights and biases provide to see which model on a certain set of hyperparameters is the best for you to then deploy to the public. And then finally, if you're looking for any interactive learning resources, I encourage you to use, for example, Kaggle datasets and tutorials. That's where the dataset was retrieved from for this presentation. And I encourage you to look at the website, take a look at some of the datasets that they offer, and see how you could use maybe some of the datasets or maybe other datasets online for your own CS50 final projects. All right, now with that, thank you so much for watching. I hope you've learned a little bit more about the data science workflow and some of the key techniques that you can employ in your own CS50 final projects. Thank you so much for watching and best of luck with your projects.